x is normal, and the ML estimator for your population mean is just a sample mean, and you can calculate the SE of the sample mean, which is sigma over square root of n, and this is approximately S over square root of n, the sample standard deviation. You can also bootstrap the SE, and this is something that you can always do parametrically or non-parametrically. But there's another way. You can use an approximation based on large sample properties of MLE. So this is especially great if your sample size is relatively large. So the big theorem here is that the MLE, it's asymptotically unbiased and normal. So for a large sample size, your estimator is approximately normal with its expectation is just the true value of theta, and the variance is something involving Fisher information that we need to discuss. What is Fisher information? What does it measure? So so Fisher information tells you how much information a single observation is giving you in determining your parameter theta. So we can look at two examples. What do I mean by how informative it is? So let's look at an example of informative and uninformative. So say that x is normal mu1. Then we have this log likelihood. Say that x is normal mu25. Then we have this log likelihood. So now we'll see why the first case here is informative and the second one is uninformative in a second. So I basically want to see how much information a single observation is going to give me about my unknown parameter mu. Now to generate samples, observations, I'm just going to suppose that mu is 5. Okay, so let's suppose we know that mu is 5, and so I'm going to generate these samples from N51 and N525, and I'm going to plot the log likelihood as a function. So the log likelihood is a function of mu. So here's what we get. So looking at the top, so each of these trajectories that you see is a different observation. So it looks like we have 1,000 observations here, and for every observation that we have, we would calculate, so we have a different log likelihood, and when we do an MLE estimate, our estimate is the mu value that maximizes this curve. So in other words, the mu for which this log likelihood peaks. And so in the top one, you can see there's a fairly small range of possible mu values. In the bottom one, there's it's hard to tell what the peak is for any given curve, right? There's a wide range of possible mu values. And so you can think of each trajectory or each observation as a vote for what the true value of mu is. So, okay, so how do we measure that curves have a tighter peak? So you can see why the top one is informative. Our x values are pretty informative about what mu value peaks the log likelihood. And so what does it mean to be informative? And so we can answer this question by looking at the slope of these trajectories. So these two pictures on the left. Oh, okay. So the top picture on the left is for the informative case, and so for different values of mu, you can see the variety of slopes that we have for these trajectories, right? So here's on the right is the histogram, say for the blue one, for the green one, for the red one. You can see that they're pretty spread out. If you compare that with the uninformative trajectories, so here, right, there's we didn't even draw the histogram there. It's all of the slopes are the same. There's no variation in what the slopes are. So our main thing that we notice is that as the curves are more peaked, in other words, in the informative case, the scores vary more widely. In other words, we have a wider histogram. And in particular, if you look at the middle one here, you can see that the center of the histogram is 0. Right? The center of the histogram is 0. We have some slopes that are positive, some slopes that are negative, but on average it's 0. And so when our evaluation of mu is 5, which is the true value, we see that the expectation of the scores is 0. Okay, so from these observations, then we can make a definition. The Fisher information is the variance of the middle histogram. Okay, so this histogram in green here, the variance of this histogram is the Fisher information. Okay, so that's the definition given here. Because the expectation is 0, you can write it in this alternative form, just noting that the variance of A is the expectation of A squared when the expectation of A is 0. Furthermore, if the log likelihood is twice differentiable, then we can write the Fisher information alternatively in this form here, which is very nice because the second derivative can be interpreted as curvature. This is sort of the most enlightening form of Fisher information, and it basically interprets it as the average curvature over all the values of x in x. So you can say that the Fisher information is the average curvature for the different possible values of x. You can write that as minus the expectation of the second derivative of the log likelihood. So this is our working definition for Fisher information. So now the main points are that if you have a number of IID random variables with density fx given theta, then the ML estimator is approximately normal with mean theta and Fisher and variance 1 over n times the Fisher information. And secondly, we have something called the Kramer-Rao inequality, which tells you that the variance of your ML estimator is greater than or equal to 1 over n times the Fisher information. So again, this is very nice because it says that 1 over n times the Fisher information is a lower bound for what the variance of your estimator is. We say that if the variance equals this lower bound, that the estimator is efficient. And furthermore, ML estimators are asymptotically efficient. So this follows from right here, right? This is the Kramer-Rao lower bound. So in the case when n is large, the variance is reaching that lower bound value. So that's all great. So we finish off with a big example that sort of shows a lot of this in play. Okay, so let's take a look at an example where x is Bernoulli p, in other words, binomial 1p, and so I'm going to take a bunch of these Bernoulli p's, and I'm going to find its Fisher information. And so that involves calculating, right? This is right. So we need to calculate the log likelihood, the derivative of the log likelihood, the second derivative of the log likelihood, all for a single observation, mind you. Find the expectation of the second derivative, and then we need to take the expectation, and so it's minus the expectation of the second derivative. We get this formula, 1 over p times 1 over p1 minus p. And so we can find the standard error for our estimator by finding so we find the standard error. Let's find the Kramer-Rao lower bound for that standard error. So in other words, we need to find 1 over n Fisher information, and so that's just a calculation. So it's p1 minus p over n, and so we know that the variance is going to be larger than this lower bound. Okay, so let's actually calculate what the estimator is, right? So we have a bunch of data, IID binomial, and so it's a fairly straightforward calculation to show that. So it's fairly straightforward to show that that the estimator is going to be the average of these estimates. And so what's the variance of the estimate? So just straightforward calculation, you can actually see that it is the Kramer-Rao lower bound. It's p1 minus p over n. So that's kind of cool. So in this case, our estimator is efficient. And finally, you can just calculate the confidence interval. So from above, you can see that you can calculate the SE, or an approximation of the SE. It's the square root of x bar 1 minus x bar over n. And so since the since our estimator is approximately normal, x bar by the central limit theorem, or if n is large, it is normal, our CI will have this form. Okay, so that wraps up today.